Thank you, Ozzy. So I'll try to keep the time. All right. So hello, everyone. Thank you for having me. It's a pleasure to tell you about this topic. I mean, I'm a big fan of neutron stars, which I've seen in the program is a big topic of this school. And I would say that this topic, when I came to know it, I would say I caught the virus of this topic, and maybe you would catch it too. Why is that? Well, I think that this is because it's a very rich problem with many outstanding questions in the very different fields of physics, I would say. I mean, if you think about it, you have to consider electrodynamics, you have to consider quantum electrodynamics as well, quantum effects, general relativistics effects, and plasma physics. And all of this with a touch of computational astrophysics, and then you have a wonderful cocktail and fascinating cocktail to make great science. So this is what I'm going to talk about today. But first of all, let me introduce myself. So my name is Benoît, Benoît Cerut. I'm a researcher at the CNRS, that is the National Research Center in France. And I'm affiliated as well with the University of Grenoble, that is located in the French Alps, not very far from Torino on the Italian side, and Geneva on the Swiss side. And so my main research interests are neutron stars, of course, but also interested in more generally how do you accelerate particle in the universe? What are the processes that accelerate particle, shock, reconnection? So I think you had a talk by Giovanni before that was referring to these different processes. So I like to understand these processes around compact objects in particular, and whatever comes out of these objects, relativistic winds, relativistic jets, any relativistic magnetized outflow. And so today the focus of the talk will be on neutron star magnetospheres. So we are going to zoom in the innermost region, but still outside of the neutron star crust. And we're going to look at these plasma processes coupled with the magnetic field of the neutron star. And I'm going to explain a bit the current model of how do we understand the basic feature of a magnetosphere. And in the second part, I will explain to you why such objects are a great environment for accelerating particles. And this is another reason why I came to get interested in these objects, because they are wonderful nearby laboratories to study particle acceleration. Okay, so some of the introductory material you may have seen already during this week, but I suppose that's okay if I say it one more time. So as you probably know, neutron stars were discovered in 67, 68 as radio sources with a very short rotation, the very short period that was interpreted very quickly as a rotating compact object. And that like the mental picture we have is like just spinning some stuff like lighthouse effects that would produce this pulsation of light by every period. And so, as I was saying in the introduction, these are wonderful laboratories for many different aspects. You have these extreme densities, you have this, the most intense electromagnetic fields in the universe, and there are also wonderful objects to test GR, and that's actually how gravitational waves were first detected, at least indirectly, thanks to pulsars. And so this phenomenon, the phenomenon of pulsar, that is, as we know today, a spinning neutron star, this phenomenon was actually predicted just before the discovery of pulsars themselves by Pacini, who asked himself the question of how do you power the Crab Nebula, the supernova remnant, that you need to have an additional energy that is being pumped into the nebula. And he came up with this idea that you should have this rapidly spinning neutron star that should be pumping energy into the system. And that's what I think is remarkable in this, is that since you have a spinning object with magnetic field, you should expect to see electromagnetic radiation at low frequency, and that's basically the pulsar phenomenon that was predicted just there. So as you can see, this was really very quickly realized soon after the discovery, that we basically understood pretty much all the players in the game here. Nevertheless, you see, we are still we're 60 years later, and there are still many problems that we need to solve that are not fully understood, but we are making great progress, and that's basically what I will try to describe today. What's wonderful about pulsars? So you see, everything is wonderful with pulsars, and another thing that is remarkable, I would say, is the fact that you see exactly what your energy reservoir is. What I mean by this is that you measure the spin of the star, so you have the total energy, mechanical energy stored in the rotation of this solid body. But you have another information, is that the pulsars do spin down. And what this means is that by measuring the spin down, you measure directly the total power that this object is releasing outside. Whether you see this power or not, in terms of radiation, in terms of light, that's a different story. So basically, you see that the star is losing energy in the environment. And so this energy must go somewhere. And what's great about these systems compared to many other high energy sources, that you know exactly how much power you have a precise measurement of the power released by the star. Okay, so you know exactly what you start with. And that's really key. And so the way this is usually understood, and I'm sure you've already seen this, but just to make sure we're on the same page, that you assume that part of this energy is being lost by dipole radiation, meaning that you have this magnet, this dipole magnet that is spinning at some angular velocity omega, with some angular magnetic moment, mu, with some obliquity chi. This is the angle between the rotation axis and the magnetic axis. Then you can infer, using this model, and assuming that all of the spin down power measured is going into this power, then you can infer the kind of typical characteristic energy. So this is what I'm writing here. The typical magnetic field strength, so the magnetic moment that you need in order to match the spin down power. And so you can get this way an estimate of the surface magnetic field. That is here normalized to P and P dot, so assuming P equal 1 and P dot equal 1 second per second. And so you can also measure a characteristic age of the pulsar by doing the ratio of these two quantities, the period and the time derivative of the period, so the slowdown of the pulsar. So these two quantities are being measured, P and P dot. And so this is usually how this is presented in the whole population of pulsars. In this diagram as P and P dot, you see the P dot is typically on the order of 10 to the minus 14, 15 for most of the pulsars. That lies in the kind of 0.1 to 1 second term of rotation period. And from this, you can infer from the dipole formula the surface magnetic field. So you see this is ranging from 10 to the 13 Gauss to 10 to the 11 Gauss for the bulk of the population that is believed to be young systems with characteristic ages. You see that is on the order of thousands to millions of years, as you can see from this blue dotted line, again using this formula over here. So this is where most of the non-pulsars, radio pulsars, but also gamma ray pulsars I will be talking about later on are lying. But there is also this other part of the diagram you see with much lower P dot. So they slow down at much lower rate, but they spin at much higher angular velocity. And this is the population of millisecond pulsars that we believe are systems that are in binary with a companion that has spun up during the binary evolution. The pulsar over here that can be many millions or even billions of years in terms of characteristic age. So they are thought to be much older systems, weaker magnetic field, but spun up by accretion events. And then on the other side of the diagram over here, you have slower rotators. So you see we're talking about several seconds, tens of seconds for the spin period. But we're talking about much stronger spin down power, resulting in the characteristic magnetic field strength that can be on the order of 10 to the 15 Gauss. And this system have a very different phenomenology that I would not describe in this lecture. That has to do with the magnetic eruption that are dominant in the case of magnetars, where essentially the mechanical energy, kinetic energy stored in the rotation of the star is smaller than the magnetic energy density in the case of a magnetar. While in the case of neutron star, the main energy reservoir is in the rotation. So we usually talk about rotation-powered pulsars as the young population or the millisecond population, and the kind of magnetic field power neutron stars as magnetars. But again, in this lecture, that would bring me too far to treat also magnetars, so I'm going to focus the lecture on this rotation-powered population, so on these two main systems. So one thing to realize is that pulsars also radiate throughout the entire electromagnetic spectrum that is accessible. So it can go all the way from radio, where they were discovered, all the way down to radio, and all the way up to gamma ray radiation. And I will precise what I mean by gamma rays, because gamma rays is a very broad spectrum. And this is an example of the Vela pulsar. It's well-known pulsar. You can see the nebula of the Vela pulsar. Radio, you see here, this is in the optical, we see also pulsations. There are two periods here shown to show the periodicity of the signal. X-rays and you see like gamma rays, meaning here above 100 MeV. So what this is telling you is that this is probably not just dipole radiation that you see. It's not just the low frequency emission that was envisioned initially by Paczynski, but in fact it's much more than this. And if you want to explain this kind of high energy radiation, X-rays, even optical and gamma rays, you need to have actually relativistic electrons, relativistic particles, or more generally relativistic plasmas near the neutron star in order to explain such energetic radiation. And this is an actual spectrum, spectral energy distribution, USU, of the Crab pulsar. So this is not the Crab nebula, but we are just focusing on the pulsar itself. So as you can see, the Crab nebula here. but just the energy coming out from the magnetosphere that is in the form of pulsations. And if you do this, you can see indeed that radio is a very, very small fraction of the energy of the radiative output, but most of it is actually being emitted, you see, at high energy. And if I look at the gamma ray band, that would be this magenta or pink region over here. You can see this is where it peaks, essentially, where the gamma ray emission is peaking. So this is telling you again that you have very efficient particle acceleration, and that the spin down power doesn't go into the radio, but actually goes most of it to the high energy band. And there's been, and still is, today an interesting development from the observational side is that we can see pulsars all the way to TeV gamma rays, and this is new, well, relatively new in the sense that we've seen like the crab pulsar, as is shown here in these gray dots. You can see the crab pulsar spectrum that is kind of continuing all the way to 1 TeV. That's 1 TeV over here. But what is new with the Vela pulsar in particular is that they have seen, and the Vela are here, they thought that basically there would be nothing above 100 GeV because you see the spectrum in the GeV band is peaking somewhere around 1 GeV and then rolling off nearly exponentially. And what is new is that they found a new component. You see that is coming up here that seems to be disconnected from the GeV component, at least spectrally. That seems to indicate that you may have two relative processes, a bit like in an AGN, where you have synchrotron radiation in the X-rays, radio X-rays, and then inverse Compton emission in the gamma ray band. So it's possible that's what people are thinking about nowadays, that you have this component that is, and I will argue later on that is mostly synchrotron radiation over here, that explains the GeV component. And then you have this extremely energetic, you see we're talking about 20, this is 10 GeV over here, all the way to 20 eV at least, maybe even more, gamma rays that come from the magnetosphere. And this is really, really challenging. And this is still an open question, by the way. I will not give you an answer today of what this is. But stay tuned, because there will be probably many more that will be discovered in this band, in particular with the advent of the CTA observatory. And what I didn't mention here, you can see the pulse profile in the GeV band, and here this is in the Hess band, so above 5 TeV, where they detect at least one pulse. See, there were two pulses at low energy, that is just one single pulse here. Okay, so let's go back to gamma rays, because the gamma ray band, and I'm talking here this time the Fermi lat band, so 100 of MeV to 100 of GeV gamma ray photons. The reason why I'm talking about this band is that, as I've told you before, this is where the most of the spin down goes. It goes into high energy gamma rays. So this is a very important band to observe pulsar. And if we want to understand pulsar, we have to understand gamma rays. That's basically the message. And also the reason why the gamma ray has been playing an important role is that we see many pulsars. And this is actually, in terms of population, this is the most important population of individual sources in the galaxy. And this is, you can see the update from 2023, from the last catalog from Fermi, where they discovered about 300 pulsars. And you can see the number of gamma ray pulsars as function of time. This is the solid black line over here, just steadily increase over the years. So we keep on discovering new systems because of better analysis techniques, better multi-wavelength survey, in particular in radio. like for instance, the FAST telescope in China, or like the Meerkat array in South Africa. They play an important role in discovering new gamma ray pulsars. And so, as I told you, most of the spin down goes into gamma rays, and that's basically what this plot is showing. It is showing the radiative efficiency, so how much power you have in the gamma ray band, in the Fermi band, so above 100 MeV, and you divide this luminosity to this apparent isotropic luminosity to the spin down power, this E dot. So the one that you measure from the spin down of pulsar. And when you compare the two, you can see, well, there's lots of scatter and lots of uncertainty due to the fact that we don't really know the distance very well. We don't really know also how big the beam is of the radio of the gamma ray emission. But if you put all in all, you still have most likely a sizable fraction of the spin down power that goes into the Fermi band. So I'm talking about 1 to 10%, maybe even more. And to me, this is arguably the most surprising thing. The reason is what's being shown here. So remember again, the power that you have initially is the spin down. Okay, and this is measured very well. Very high precision. So on this side, we're on solid grounds. That's your reservoir. And in the end, you are measuring your photons, okay, in any form. Gamma rays, it can be anything. Mostly, let's say gamma rays for simplicity here. And you must end up with, well, maybe it's 10%, not 100%. But you must have, let's say, 10% in the end in form of gamma rays. But you need to, from spin down to non-thermal radiation, you need to do something. You cannot just transfer E dot directly into radiation. What you need to do first, and that's what I will explain in this lecture, you need to transform first this mechanical energy in the form of electromagnetic energy, or in the form of Poynting flux. And this, you need to do this with high efficiency. The next thing is you cannot just convert Poynting flux into non-thermal radiation or into a broad range of energy like this. You need to dissipate this energy, this electromagnetic power, in the form of energetic particles. Or in other words, you need to accelerate particles, and you have to tap energy from the fields that you dissipate, and you gain individual kinetic energy on the particles. Okay? That's what I call the process of dissipation. And that's actually where most of the difficulty lies in. That's what is the microphysics? What is the dissipation processes that will convert this energy in the form of high energy particles? And that's where plasma physics comes in. Okay, that's the difficult part. Then once you have your high energy particles, then you apply the radiative processes that you have learned today. I think there were multiple lectures on radiative processes to convert your energy in the form of radiation. Okay, and this is known. So the main uncertainty is here. Okay. Okay, and so before we dive into the details of what's happening, we believe that these magnetospheric processes occur in many different environments, or in many different, let's say, it explains different astrophysical phenomena. So pulsars, that's the topic of today. But also accreting X-ray pulsars that you have seen, I think, yesterday, if I remember from the program. You have also accretion that is interacting with the magnetospheres of the neutron star. Magnetar flares, where the magnetosphere of the pulsar is also involved in the emission of this burst of light. We believe that more and more that fast radio bursts may also be powered by the magnetosphere of neutron stars, and more specifically of magnetars. The Pulsar with nebula processes, so this is at much larger distances, but this is where the plasma, the wind produced in the magnetosphere, then interacts with the medium, and you can see the nebula a bit as a calorimeter of what the magnetosphere is generating. Essentially, you should find the spin down in the end in the nebula. But also in binary compact object mergers, so if you have mergers between a neutron star and a black hole, or two neutron stars, you're going to have activity of an intense magnetospheric activity by combining the orbital motion to the intrinsic spin of the stars that could induce possibly a precursor emission before the two stars actually merge. And this is also another field of interest. Okay, so let's go back to the basics. In the Google Drive, you will find the slides that I'm showing you here, but you will also find, and I will show you this here, my lecture notes in the form of a short PDF of 5 pages over here, over which there will be proof of some important results from the theory of pulsars. We'll not go through them, I will not have time, but I leave it to you such that you can rederive all of these important expressions, okay? And there will be notes in the lecture notes. So it's going to be proof 1, 2, 3, 4, 5, I think, or 7, I forgot. And this will relate to the proof in the slides. Okay. So if you think about it, I told you that a neutron star, pulsar, is just a spinning dipole, essentially, and this plasma around it, and that's it. Okay, that seems to be very easy, a very easy problem, and that's the catch. I mean, this is indeed very well posed. We know exactly how much energy we have to begin with. We know what we're talking about. But the problem is super complex and very rich, as I've wrote here, richer than you may think at first sight. And the reason is because you are going to couple all of this physics together. So plasma physics is going to make all the beauty of the problem, or the diversity, or the richness of the problem. And to try to illustrate a bit how we think a pulsar is spinning down in the presence of a plasma, I will take this analogy that we usually use to explain how pulsars spin down. It's called the unipolar inductor. And I will use the case of a Faraday disk. It's kind of what you do at a university experiment. You take a disk. Let's say that my star now has been flattened into a disk, just for simplicity. This disk has a radius r, and I will assume that this disk is perfectly conducting. Okay, it's a perfect conductor. And I'm going to immerse this disk into a large-scale magnetic field. Let's say it's uniform. Okay, B, uniform B. And for simplicity, I will assume that this magnetic field is aligned with the axis of this disk. Okay. So if the disk is at rest, it's a perfect conductor, my electric field in the disk should be 0. Okay. And I will assume at this stage that there is no that my disk is in vacuum, or let's say surrounded by an insulator. Okay. All right, so, but now if I spin the disk, so let's say I spin to an angular velocity omega, and this omega, let's say, is the, so you have to imagine the angular velocity of the star, obviously, then the thing is different. Because then in the lab frame, so in our frame, we are looking at this disk that is spinning, But now if you sit into the disk frame, your charges in the disk, you still want this co-rotation, the electric field in your frame to be zero. Okay, so the E prime in the co-rotating frame should be zero. But now, if I want to look in the lab frame, in order for the electric field to be zero in a convex frame, you have to induce an electric field in the lab frame in the form of V cross B minus V. V is the velocity of, let's say, an electron in the disk, cross B, the perpendicular magnetic field. And this V cross B velocity is necessary in order for the charges to be in correlation with the disk. Okay, and thus, once they are in correlation, they will not feel any electric field, they will not move, right, in the co-moving frame, co-rotating frame. So in the lab frame, the disk must be polarized, right? There is a radial electric field in the lab frame. So what this means is that the rotation of the disk has induced motion of charges, so electrons, ions in the disk, mostly electrons in my case, in order to cancel the electric field in the co-moving frame. Okay, so that means that I have a potential difference in the lab frame between the core of my disk, that is mostly where most of my electrons are going, and positive charges where I'm depleted in terms of electrons. So that would be the end of the story if I were in vacuum. Okay, and I could indeed measure potential difference between the core and the outskirt of the disk, and measure currents. So now, if I go to a spherical symmetric version, I should expect this. I should expect a poloidal component of the electric field from the pole, so the center of my disk, if you wish, to the outside, so to the side, to the radius of the star over here, with positive charges in the equator. Now, let's say we are not having a uniform magnetic field, but let's say a dipole. We would not change very much the picture. It would remain polarized, but the distribution of charges would be different than a uniform magnetic field. But that's the same idea. Okay. And now, if I measure the potential difference in vacuum, I should measure something on the order of 10 to the 18 volts. If I take as numbers an omega that would correspond to 100 millisecond per period, and a canonical magnetic field of 10 to 12 Gauss, so basically a Young pulsar. But I told you this is valid in vacuum. But now, if you think of the field strengths of, again, my canonical pulsar, this was realized by Goldreich and Julian, and you ask yourself, what should be the electromagnetic force applied to any charges at the surface, let's say an electron? And how does it compare to the gravitational force, gravitational pull that keeps the star together? And what they found is that this is an astronomically large number, meaning that for this pulsar field strength, you should expect that the electromagnetic force, so the electric force parallel to the magnetic field lines, in particular at the poles, should be really, really completely dominated the force balance over the gravity. So what this means is that, in other words, you're going to start pulling off charges, electrons, ions, nuclei from the crust of the star, such that in the end, you're not going to do this indefinitely. You're going to do this up to the moment where this E parallel is going to be screened. Or in other words, you're going to pull charges, and as you do so, you are going to start to screen the electric field induced by the rotation. Okay, and you can compute what's the minimum amount of charges you need in order to screen this electric field, beyond which you are going to stop pulling off charges from the surface of the star. And you can show, and you will see in notes, proof 1, that this is the dot product between omega angular velocity, and the magnetic field. And if you use this as a dipole, you find a distribution. It will depend, you see, on the colatitude angle theta and the radius as to the power -3. And it depends on B and omega, so the dot product over here. So what this means is that, in principle, I should get a structure that looks like this. I should have charges, so no vacuum. And if you do the calculation, that's not an easy calculation. It's not analytically feasible, and this was done numerically by different approach. I'm showing you some of the similar papers on this. You should expect some stuff like what is called an electric sphere, meaning that you should have here for an aligned rotator. I assume that the magnetic moment is aligned with the rotation axis. You should expect to have a structure with electrons in the poles of the star, and mostly positive charges, so ions, forming some stuff like a belt around it. That's what predicts this formula over here. But if you do this, basically, that's the end of the story. Not much is going to happen because you are not going to drive currents. But we need to drive currents in the system to make the system electrodynamically active. That's an example of a PIC simulation. This was a drawing, and this is an actual result from a simulation. You see, you form this PIC simulation, this dome of electrons and this kind of equatorial belt of positrons or positive charges. Here it was positrons. But this is not the end of the story. Because what we expect is that these particles, as they are being pulled off or ripped off the surface of the star, they are going to be accelerated to very high energies thanks to this parallel electric field to the magnetic field, to the local magnetic field, meaning that charges will be accelerated to very high energy along curved field lines, and as they do so, they will radiate via curvature radiation, producing high energy gamma rays. But these gamma rays are opaque because they will not escape because the magnetic field is so strong that they will absorb by magnetic conversion, so gamma B process, the gamma rays and form electron-positron pairs. And these new pairs will be then able to be accelerated by the same electric field, producing additional gamma rays via synchrotron or curvature radiation, which themselves could be absorbed in the magnetic field. And in the end, you have a cascade with multiple generation of particles being produced in the magnetosphere. So if I put all in one, what we believe is that around the neutron star, you have lots of pairs, electrons and positrons pairs being created in the magnetosphere. Here I'm making a very rapid shortcut because this process here, it's actually a mess. It's not, it's not, we haven't really been to the bottom of this mechanism of pair production in the magnetosphere. It's actually much more complex than it looks. And I will not talk much more about this, but let's assume that we can produce lots of pairs in the system. Then let's imagine that now the star is surrounded by a cloud. We have lots of electrons and lots of positrons with number density much larger than the Goldwyn-Julian density, and this minimum correlation density. Well, in that case, given that I told you that gravity is a negligible force, the equation of motion of the plasma is just, we are just left by the Lorentz force equal to 0. So this rho E plus J cross B equals 0. Meaning that we have neglected any other forces, any pressure, any inertial effects. Everything is being neglected here in the equation of motion of your plasma. And you're just left with this force-free, what is called a force-free approximation. And we're going to use this approximation for the rest of the lecture here. Almost all the rest, not completely. And so a very practical formalism for what follows is to use axisymmetry. So we're going to assume again for simplicity that the problem is axisymmetric, meaning that again my magnetic axis is aligned with the rotation axis of the star. And if you do this, you can describe entirely your magnetic field, B, in the system with two quantities, two scalar quantity. The magnetic flux function, this psi quantity that is defined as the magnetic flux that is crossing through a sphere or a spherical portion of your coordinates, and another function, another scalar called the current function, and this will quantify the amount of current J crossing through the same surface over which I'm defining the magnetic flux. So this is standard what to do in axisymmetric flows in MHD. So I'm reusing this formalism. And what you can show is that in the context of axisymmetric steady state, we'll assume it's all steady state, force-free ideal MHD flow, you can show that the magnetic field line, so imagine you have this magnetic field line anchored into the surface of the star. If the star is spinning at some angular velocity omega, well, each field line, B, will actually represent the omega will be constant along a field line, because you can show that B dot the gradient of omega is equal constant. So if you have the magnetic field here, the magnetic field line, it is perpendicular, the dot product tells you it's perpendicular to the gradient of this magnetic flux function. Okay. So what this means that indeed, the omega, so it's the same as here, the omega, meaning that any field line here, poloidal field line, will be a line of isorotation. And the other thing, that's why I got confused, is that the field line, you can show the same thing, that you can have the gradient of psi and the dot product with the poloidal field is equal to 0, which means that every poloidal field will be an electric equipotential, which is also quite convenient. So if you look at the dipole, each field line is at a different electric potential. Okay, so the more you cross field lines, the larger the potential difference would be. Keep this in mind, because this will be important for particle acceleration, because obviously we need particle to cross several field lines in order to gain a large potential. Okay. Now, if you combine these two aspects, so I told you axisymmetry with the force-free condition. So if we take the two conditions, we assume it's steady state, then, and there are many steps, and I encourage you to look into the notes, you can get a single equation. You see, that looks like this, that we call the Pulsar equation. It's a form of a Grad-Shafranov equation. We see that you have an equation with partial derivatives that involve the magnetic flux function, the current function over here, and the light cylinder radius over here that is related to the angular velocity of the star. Okay. So by combining these two plus steady state, you can show that you have a single equation like this. And in principle, if you solve for this equation, you should get a solution for the whole magnetosphere. And for many years, people have tried to solve this equation analytically. Unfortunately, for a dipole field, even in axisymmetric steady state, we don't know an exact analytical solution to this problem. And this is why numerical simulation have come into play. And that's thanks to the simulation that we've made a lot of progress. The light cylinder that I've just mentioned. So you see, this is defined as the speed of light over omega. This is a virtual surface, cylindrical radius, within which, if you want to be in co-rotation with the star, you can do it with a speed smaller than the speed of light. So if you imagine that you go around the pulsar, if you're inside the surface, the speed of co-rotation is subluminal, so it's possible. But if you go beyond the surface, you have to go faster than the speed of light if you want to keep up with the rotation of the star at such distances. Okay. And this distance, you can define it to any rotating objects. And for the case of pulsar, what's interesting is that this surface is relatively nearby, right? Because the spin is high. It depends just on omega, after all. And if you take a canonical pulsar, it's like 5,000 kilometers. So it's much further away to scale. This is, we say, this is 10 kilometers. This would be way far away. But this is not like too far away for it to be important. Okay, we'll come back to this later. So I told you that this equation doesn't have a solution in the case of a dipole. At least as far as I know, there's no solutions. But you can actually there's an exact solution to this problem if you assume that you don't have a dipole, but you have a monopole, a magnetic monopole, which is something that does not exist, right? But it turns out to be quite instructive. And so this solution was found by Michael in 1973. And so he assumed that the magnetic flux function, this is the assumption, was a monopole, that the poloidal field solution is a monopole. And the monopole is given by this function. So that means that you have just the radial field that decays as 1 over r squared. That's it. And if you do the math, so you inject this psi into this equation, okay, then you find I. Okay, so you assume the value of psi, and then you recover what is I. Okay, you know everything else. And that's what you find. If you do the calculation, you find that I is equal to this expression. And now if I translate it in the form of electromagnetic fields, so E and B, this is my radial field, my monopole. And the main question is, what's B phi? Because I is related to B phi. And this is what you find. That you indeed, because of rotation, you start to wind up your field. You build up some toroidal component. Okay? But also, you drive the poloidal electric field, E theta, over here. And what I think is remarkable is that B phi equal E theta. The two are exactly equal in the case of monopole. And what this means that if you have a B phi, that means that you have, in particular, a gradient of B. That means that you have a curl of B. And this curl of B translates into currents, J. And you can show, in fact, that the current being driven in this monopole is exactly, you see, you recognize the formula, omega dot B, that is reminiscent to the Gauss-Julian charge density. So in the case of a monopole, you can show that the current can be driven by just Gauss-Julian charge density flying at the speed of light. You see? And there's no special surface at the light cylinder. Nothing special happens. It just crosses the light cylinder. Except that at the light cylinder, because B phi decays as just as 1 over r, and BR as 1 over r squared, at some point BR is going to be subdominant over B phi. And at the light cylinder, the two are exactly equal. And beyond that surface, so beyond the light cylinder, you're going to be dominated by the toroidal magnetic field. So to summarize, you have to imagine your magnetosphere to be filled with charges, with plasma. The rotation of the star is going to induce a toroidal component of the magnetic field, B phi, and electric currents. Well, the two are connected, they are curl of B. Okay, and these currents will be carried out by your charges, okay, by your plasma. Such that, I'm still talking about the monopole here, the field lines will look like this if you were to show them in 3D. They will look like Archimedean spiral. And then what you can do, and again, beauty says all of this is analytical. It's an exact solution. You can then compute how much Poynting flux escape the system using Poynting flux theorem over here. And you can show, and this is proof 5, a non-zero value. And this non-zero value, you see, is proportional to B squared, and basically, so the magnetic moment of the star squared, and omega squared via the light cylinder radius. So what this means is that my star is spinning down. My monopole is spinning down. It's spinning down thanks to the fact that I'm winding up a toroidal field in the system. Because I have essentially electric field that is toroidal, E theta, and I'm carrying B phi. So I have E cross B. I have a net Poynting flux that is going outwards. Okay. The fact that this is carrying energy along with the plasma, this is what will drive the wind. So beyond the light cylinder, you're going to drive this wind of plasma that will push the Poynting flux away. And the split monopole turns out to be a very good approximation for the wind structure at large distances. You will be basically dominated by a monopolar-like solution. And you can look at the kinematics of this wind. If you consider this as an E cross B drift velocity, so as the drift motion of charges in the presence of an electric and magnetic force, you can show that the Lorentz factor of the wind, you see, will increase more or less linearly with the radius, normalized to the radius of the light cylinder. And this is shown by this red curve over here. And this is the bulk Lorentz factor of the wind. So you see, it gets relativistic and ultra-relativistic very quickly. So all of this was considering axisymmetry, okay? But the pulsar is not axisymmetric. Otherwise, you will not see pulsations. And so when you start inclining a little bit with some obliquity angle, the magnetic axis, then what we expect is that the magnetic pulse from both the upper and lower hemisphere, there will be a separatrix region that will separate the two magnetic poles. And let's see. This is what I've tried to show here, is that in the dipole, basically you're going to have magnetic field line going from one hemisphere to the other hemisphere. And because of the winding of field lines, you will start to open field lines to infinity like a dipole. And you see that in the midplane, you're going to form a current sheet here because you're going to have a jump in the magnetic field orientation. And this jump in the magnetic field will generate a current sheet over here. And so in the case of an aligned pulsar, this is just a flat disk in the midplane. And in the case of an oblique rotator, you're going to form this type of a stripy, wavy structure that whose opening angle will depend on the obliquity angle. So it's going to be twice the obliquity angle. And we call this the stripe wind. That is the fact that you have these stripes that separates the two magnetic poles from the northern and and the southern hemisphere of the star. And we see this, for instance, in the solar system. Such structure exists that is called the heliospheric current sheet. Okay, so let's come back to the aligned pulsar, and let's summarize a little bit here with a simple drawing. So as I said, we have this dipole that we believe is kind of a proxy for what we believe is the overall magnetic structure, at least at large distances from the neutron star. And you have these charges all over the place. If I put the light cylinder somewhere here, well, what this means is that these charges here that are inside the light cylinder, they will be able to stream along field lines with subliminal velocity. That's okay. They can do it, and they do. But this one here, they will not. They will not be able to stream to remain in co-rotation. And so what this means is that all the field line crossing the light cylinder essentially will open up, such that the magnetosphere will look more like this. The blue field lines stay within the light cylinder. They will remain close. While field lines initially crossing the light cylinder, they will start to open up and wind up and build up toroidal field. Okay. And the same in the other hemisphere. You see these field lines have inflated, stretched, up to the moment where they have produced this discontinuity in B. And here again, we have an analog of the solar system. So I mentioned to you the heliospheric current sheet, but also in planetary magnetosphere, we have current sheets that are not induced by rotation of the planet, but more by the interaction with the solar wind of the magnetosphere with the solar wind that stretches and deform the magnetic field lines. Okay, I will skip this. I've shown you that we can measure the Poynting flux. We can predict the Poynting flux from a monopole. And in the case of a dipole, well, we don't have an exact solution, as I told you, but we can still make an estimate that is inspired from the monopole solution. And what we think is happening is that in the case of and I will show you this later on, is that beyond the light cylinder, basically we can model the field line as a monopole, as a magnetic monopole, or a split monopole. One polarity in the top and the other polarity in the lower hemisphere. And remember that in the split monopole, the toroidal field was equal to the poloidal field at the light cylinder. And so if we make this estimate, and the poloidal field, we can estimate it from the dipolar formula at the light cylinder. And if you further assume, like in the split monopole, that the poloidal electric field is equal to the toroidal magnetic field, then you can estimate the spin out power for dipole in this way. So you apply this, and then you find this formula. That is the well-known formula that you expect from force-free magnetospheres. That depends on the spin to the force power and the magnetic moment to the square power. And you see this, if I go back quickly, this is slightly different. Dependence, here it was depending on mu squared, so B squared, and omega squared. So you see it's a stronger dependence with spin. Okay, so how do we make progress? I told you that we cannot get a perfect solution, analytical solution. So people try to solve this problem using simulations. And so, and this will be the last part of my talk. I will try to limit to 15 minutes, if that's okay. And so this was done first in the context of force-free simulations, time-dependent and steady simulations. This was the effort in the early 2000s. And they were able to indeed verify and to find that the spin down power measured numerically from the simulation. So you see, we recovered the overall structure with the dipolar structure plus in the closed field line plus this radial quasi-monopolar field structure. And the same for an oblique rotator over here. Although it's less obvious to see, but you see that it tends to be more monopolar at large distances, and you see the toroidal field component here. And so they found numerically, again, it's not an analytical expression. It is an analytical expression, but that is a very good fit to a numerical result. That's why I wrote like approximately equal to mu squared omega fourth power over c cubed, which is this estimate over here. So it's a very good estimate, actually. Plus the sine square dependence on the obliquity angle. And if you may remember the solution in vacuum of a dipole, spinning in vacuum, this was the expression. You see, same dependence on mu, on omega, and sine square, except that you see there is a 2/3 in front, and there is a 1 here. The 1 is important because it tells you that an aligned rotator, so with chi equals 0, spins down, while an aligned rotator, a dipole that is aligned in vacuum, does not radiate. Right? It's by symmetry, it cannot radiate. That's what this formula is telling you. Okay, and this is the for different simulation that shows you this dependence is kind of very well verified by simulations. And so in the last part of my talk, I would like to tell you a bit more about particle acceleration, because this was kind of the point, right? We argued that there was high energy particles. The plasma was accelerated high energy to produce these gamma rays and radiation in general. So how does it work? Well, there were different hypotheses in the past where people believe that gamma rays could be emitted in different parts of the magnetosphere, the polar cap, what is called the outer cap, more or less in this region, or the current sheet. Remember where I have this discontinuity between the two magnetic poles. But the problem is with previous simulations in MHD or in force-weighted electrodynamics, you don't have the information about the particles. You don't know where particle acceleration happens because by construction you assume that everything is ideal. This was done in the context of ideal MHD. And so then you cannot tell. Where particle acceleration comes from. And so the way to go to make further progress on this question is to use a kinetic approach, where we're going to simulate the plasma from microscopic perspective. And the peak approach is just in a few words, it's a way to simulate the plasma by having a fixed grid where you evolve the electromagnetic field. And on top of this, you evolve many millions, hundreds of millions charged particles that would be moving as discrete charges on this mesh. And by evolving the particles, knowing the electromagnetic field on the grid, plus QED, meaning if you add per production, you can basically solve the whole problem of the magnetosphere. And so this game started in 2014, and for the last 10 years, more or less now, there have been lots of progress that I will summarize in the next few slides to simulate the whole magnetosphere using this ab initio model. And if I want to keep the story short, what the simulation have shown that the main culprit for producing the gamma ray emission, I think I can tell it with some relative confidence today, is there is some consensus that the gamma ray emission is coming from the current sheet. So in other words, this guy is the main source of gamma rays. Okay, so you have to add different processes. I will skip that, just lack of time. And in the end, you get some simulation that looks like this. So it's one of the most recent simulation that I have, where you can see the plasma density, the rendering of plasma density around a pulsar magnetosphere, using this particle in cell simulation. And what you can see, the star is here. This ring over here shows the inner part of the light cylinder. And you see this patchy structure over here is the current sheet. You remember this stripy structure? This is the current sheet of an oblique rotator with a magnetic obliquity of 60 degrees, so rather oblique rotator. And the patchy aspect here is it's not a numerical limitation, it's actually a physical effect. What you see here in this patch is in fact one of the acceleration processes going on is magnetic reconnection. That is a physical, it's a physical process that reconnects field lines, or if you wish, changes the topology of field lines and accelerate particles. I don't have time to go into the details of this process. This will be an entire separate lecture. But what you have to think about is that you have magnetic energy being converted, and this is our dissipation process for my little diagram. But before I will skip that. Such that in the end, we have identified, thanks to the simulation, the main particle acceleration process, that is magnetic reconnection. The same mechanism we believe is at that powers the solar corona. And that is showing you a map of the mean energy of the particle produced in the simulation. So you see the current sheet lights up. And on the right-hand side here, in this topoloidal cut, you can see the typical photon energy. And the redder it is, the more energetic this is. And we have identified this radiation as being due to synchrotron radiation, because as you reconnect your field line, you're going to produce very hot particles with high pitch angle. And as you have seen today, synchrotron radiation power depends directly on the perpendicular magnetic field, perpendicular to the particle direction of motion. So this energy is being dissipated. So this is shown here. This is showing you the amount of power in the form of Poynting flux, so electromagnetic power, for different radius as you go further and further away from the star. If you have no dissipation, you should expect this curve to be just flat. No dissipation, the energy you have in propagates out in the form of Poynting flux, and that's it. But you see that it's not the case. You have energy being lost. It's not lost in the grid or numerically by magic. It goes into particles. And again, that's what reconnection does. Okay. Okay. These are trajectories of particles from the simulation. This is quite an old movie now, but it kind of makes the point that you have this particle that is flying away along field lines, along open field lines, and you have these ones that are being trapped into the closed field lines. Basically that's the trajectory of particles, and no surprise, the trajectories look very much like field lines, because that's what they mostly do. They stream along field lines, and you recognize all the different properties. Okay, I will skip that. And what you can see here is now the time history of the same particle I've shown you, but as a function of time, their energy, their valence factor. And you can see that as soon as they get to the current sheet over here, they get like a huge boost of energy. The same for the electrons here. This one has a trajectory a bit peculiar because it comes back to the star. But basically it gets a big boost of energy as it crosses the current sheet. Yeah, and this is showing you a map in 3D of where the high energy particles are. And in red, this means high Lorentz factor, essentially. And blue, low Lorentz factors. Low energy particle in blue, high energy particle in red. You can make an estimate about the maximum energy you should get from this process. And if you remember what I said earlier, I told you that at least in an axisymmetric magnetosphere, and we're going to use this as a guide, magnetic field lines represent an equipotential, electric equipotential. Okay. So what this means is that I can compute the maximum potential drop I should expect if a particle managed to go across all of these sphere lines. It will give me the maximum potential drop. This is shown here by this calculation. I integrate over the size of the polar cap, so the bundle of sphere line crossing the light cylinder. I'm using just simply the dipole in vacuum as a formula. You see that's what I'm doing here to compute the opening angle here. And what you find is that the potential drop is proportional to magnetic moment of the star times the speed squared. And the big simulation tells me that the maximum Lorentz factor, or the typical Lorentz factor of my particle accelerated in the system, is on the order of this ratio between this quantity over here divided by the bulk Lorentz factor of the wind. So it's on the order of a few when you're close to the star. And by this kappa parameter here. And this kappa parameter is basically the density of the plasma. It's how much plasma I have with respect to the Galois-Julian density. The minimum, this number is supposed to be high compared to 1. And I like this formula very much because it tells you that the energy of particle in the end will be given by macroscopic properties, because this quantity here just relates to the property of the star. You see mu omega, and divides it to this kappa parameter that is connected to how many pairs you have produced in your cascade. You see? So it's a combination of large scale and small scale that will give you the answer to what energy you go. And I will finish in at 6:30. I will stop at 6:30, promised. So in a few minutes from now. And so, because now we know where the high energy particles are, we can then ask ourselves, where is the high energy radiation coming from? And I've already told you it comes from the current sheet. That's what this little movie is showing you. You can see that there are some irregularities that are actually due to reconnection physics. I don't have time to. There are some plasma instabilities that are triggering. You see there are some irregularities. It's really proper to reconnection. You have to also remember that the radiation, the particle are very anisotropic in the system, such that the radiation of particle will actually, that an observer at infinity will actually see, will not be the whole current sheet. You will see only a portion of the current sheet. And what I'm showing you here is an observer looking at this aligned magnetosphere. And this observer will see at a given time only this very tiny part of the current sheet, which are particles that are emitting in your line of sight, in the line of sight of the observer, because of relativistic beam. And if you do this for an inclined rotator, that's what you see. You see that the current sheet is in gray, and you will see, or you will only a portion of the current sheet will light up in your line of sight at a given time. And the time in the pulsar phase, you see. So center of pulsar phase, you see that I see first a pulse of light when the one arm of this current sheet is passing by my line of sight, and then I have a second pulse when I see the other side of the current sheet, these two structures. And we believe that this scenario is a great explanation for observation. I will skip that. That's what the model predicts. A typical different light curve for different pulse profile for different viewing angles. So each curve is for a different viewing angle of the same pulsar. And what is reminiscent of this is that most of the time you see two pulses of light, sometimes just one. And this is typical of Fermi light curves. And to prove you that this is indeed a good model, but not a perfect model, we've done a fit. We just simulated one single pulsar with different obliquity angle, and we try to see if we can explain all the observed light curve from the Fermi light. And this is what you see. This is Vela. This is other person. You have their name over here. And overall, we can explain the main features. So the phasing of the pulse, the number of pulse, we can explain all of that. But you can see that the model is not perfect. In particular, the sharpness is not great. And the main reason, this is something I did not have time to mention, is that simulations are very limited, the PIC simulations, because we have to cheat on the scales. Essentially, we cannot simulate a pulsar with an actual 10 to the 12 gauge. We have a much smaller magnetic field. So this might be an explanation for this discrepancy. And I think, perfect. I'm stopping here because I want to have time to save time for questions. And I've left you here, in addition to my notes, don't forget my notes, my lecture notes with the different proof for all of these different expressions, but also you please consult these different review papers that I've been using also a lot on my side to build up my understanding of pulsar magnetosphere. And the most recent one is this one by Filipov and Kramer. And some of the material I've shown you in this lecture is in the review I wrote myself with Andrei Belobodov. Well, now it's back to 2018, I think. Thank you very much for holding up all the way to the end of my lecture. You must be tired by now.
Thank you so much.
Thanks, Benoît, for that great talk and enlightening us about the particle acceleration and pulsar magnetosphere. So maybe we can have a short question if there are any here. Yeah, could you please come here? So we have one question here from Kai.
There's a lot of material.
So in the beginning of your talk, you showed that this is a nice continuous spectrum that's consistent with synchrotron. But when you looked at say the pulses in the different bands, they look completely different. So does this mean they are probably emitted from very different regions? And could the messiness of these pulses even say related to the conditions there, that there are more free charges and so on?
Yes, absolutely. The picture is very complex if you look at different bands. So in radio, they will show you different features of different phase, different pulse profile, which we think is mostly related to the discharge of per production in the polar caps. But as you pointed out, like in the Vela case, we have UV, we have X-rays, the Crab also, we have the pulse profile in many different bands. And they show very puzzling features. Sometimes they show even 4 pulses that doesn't seem to be necessarily connected with the current sheet. So there's a lot more to understand, indeed. Yeah.
Thank you so much.
Thank you.
Thanks again. And Yavuz Hocam, do you have any questions or comments that you want to add?
I can ask anytime. If there is a student who wants to ask.
Okay. Are there any questions? No. Okay, no. Seems like everybody wants to go for dinner.
Which I can understand, yes.
We are hungry.
It was a long day for you guys.
No, thanks again. Thanks a lot for your really nice talk, which was quite enlightening for us. And thanks also for the documentation that you shared with us, so we can share with our participants.
Yeah, you're welcome to contact me if you have questions on the material. Again, I know it's a lot of material, so feel free to contact me.
Okay, thank you very much again. So,
thank you. Have a nice day.
Okay.
Thank you. It was nice seeing you.
Okay.